Number one, according to an article on the Guardian website, a British woman born in 2003 has a 0.27% chance of living at least 100 years. Okay, so what this deals with is what our fundamental understanding of probability is, and that is if you do something many times. So you take a very large group of women that were born in 2003, and you take the number of those women that lived past 100, and you should get something close to 27%. So what I did was I set up a little simulation over here using the law of large numbers applet. Okay, and I changed the percent that Miss Gayless would make a basket to 27%. So that just mimics the living past 100. Okay, now if I take 50 shots, all right, you'll notice that I made 10 out of 50. So that would be, if my sample was 50 women, 10 of them lived past 100. Okay, that's only 20%, and it's supposed to be 27%. What this means is, as this number on the bottom gets larger, that percentage is going to get closer and closer to 27. So here I did 100 shots, and I made 23 out of them. So if I had 100 women born in 2003, I would expect this says 23 of them lived to be over 100. So we're not yet at 27. Okay, if I go up to 150, if you look over here, I get 23.3%. And if I go up to 200, I get 51. And the larger I make this denominator, the closer this percentage is going to get to 27, but it's not there yet. So when it says, suppose you randomly select 200 women who were born in 2003, will exactly 54 of them live to be at least 200? Well, the question becomes, well, how did you get 54? Well, if we use our model, okay, we know that if we had 200 women, and our model says 27% of them should live past 100. Well, if I take 0.27 and I multiply it by 200, I get 54. Okay, but it's not going to be exactly 54. Like in our little simulation over here, we got 51. We didn't get 54. But if I made this number a lot larger, then that would be a better indicator of how many I would get. The percentage would get closer to 27. So to answer this question, will exactly 54 of them live to at least 100? Probably not. Okay, around 54, but like in our example, it was 51. So I'd say no. Probability describes what happens after many more repetitions of a chance process. So you have 5 friends, all happen to be females born in 2003, assuming that the survival of each one is independent of the other. What's the probability that at least one of them lives to be 100 years old? Well, what we learned was there was a quick way of doing at least one, and it was called the complement rule. And to get the probability that at least one makes it to 100, I would take 1, subtract the probability that none of the 5 make it to 100. All right, if there's a 27% chance that somebody lives to 100, then there's going to be a 1 minus 27% chance that they don't. So that's the probability of not living to 100 if you are in that group. Okay, so I want to find out the probability of none of them living to be 100. So to do that, I'm going to take the probability that the first of my 5 friends doesn't make it to 100. So that would be 0.73. Since these events are independent of each other, so whether the first person dies before 100 doesn't influence the probability that the second person dies before 100, or and so on. So the and becomes a multiplication. So the probability that the second person doesn't make it to 100, the third person times the fourth person times the fifth person. Okay, that all becomes 0.73 to the fifth power. So if I go up here where I started, I'm going to do 1 minus 0.73 to the fifth power. All right, here's our answer on our calculator, and it says round to 3 decimals. So the 2 is the number that might get rounded. I look at the 6 that says round the 2 up to a 3. So my solution here will be 0.793. And that's my answer for the probability that at least one of my friends lives to be 100 years old. 2. Choose a new vehicle sold in the United States in 2019 at random. The probability distribution for the type of vehicle chosen is given here. What is the probability that the vehicle is a crossover? Well, we know that if we take these 5 probabilities, they have to add up to be 1. So we're going to take these 4, add them up, subtract from 1, and get the crossover. So there's the 4 that we knew, added those up, subtracted that sum from 1, and we get the probability of there being a crossover to be 0.41 or 41%. The second part, B, says, given that the vehicle is not a passenger car, what is the probability that it is a pickup? So as soon as we see that word given, that means that we're going to be working with conditional probability. Okay, so over here is our formula for conditional probability, and that is the probability after you know something has occurred. So if you know that it's not a passenger car, then what's the probability that it's a truck? Okay, so if we wrote, this would be written as the probability that it is a pickup truck given that it's not a passenger car. So you automatically know it's not a passenger car. So first we'll do the denominator, not a passenger car. So if I go up here, I'm going to add up the probabilities of these 4 categories that are not passenger cars, and that's going to be my denominator. Okay, now to get the numerator, the formula that I use for a pickup and not a passenger depends on whether or not being a pickup truck and not a passenger car are independent or dependent events. Okay, independent meaning that the probability of one does not influence the probability of the other. In this case, these 2 events are dependent, and here's why. If I know that I have a pickup, then I automatically know the probability of it not being a passenger car. It'd have to be 100% or 1 because pickups aren't passenger cars. So these 2 events are not independent of each other. So to get their probability, I take the probability of A, which in this case is the pickup, and then I'm going to multiply that by the probability that it is not a passenger car given that it's a pickup. Well, the probability that it's not a passenger car when you know it's a pickup is going to be 1. So that doesn't change the numerator at all. And now I add up my denominators and then divide it out. Part C, what is the probability that it is a pickup truck, SUV, or minivan? So this is using the word or. Okay, so when I want to find it's a pickup truck, so I'm trying to find out if it's the probability if it's one or the other, which means we use our addition rule when we have the word or, and the events are mutually exclusive, which they are. You can't be a pickup truck and an SUV at the same time. So when I have an or statement, I use my addition rule and I add up the 3 probabilities to get 0.31. Okay, part 3. Darren's teacher has assigned each student in the class an online quiz made up of 10 multiple choice questions with 4 options. Darren hasn't been paying attention in class and has to guess at each question. However, his teacher allows each student to take the quiz 3 times and will record the highest of the 3 scores. A passing score is 6 or more correct out of 10. We want to perform a simulation to estimate the score that Derek will earn on the quiz if he guesses at random at all of the questions each of the 3 times he takes a quiz. All right, so you have 10 questions, and we have to have a way to simulate 4 options. So one way that you can do that is if you want to create some sort of model that would simulate 4 options, then we could use the numbers 1 through 4. Okay, if we randomly choose a 1, that means that he guessed correctly. And if the numbers 2, 3, or 4 pop up, that means that Darren guessed incorrectly. So we could put 4 numbers in a hat, draw one out, see what it is, and that would tell us if he guessed correct or incorrect. And we'd have to do that 10 times. So we did that with a random number generator right here. Okay, I put in, I told it to pick numbers between 1 and 4, and anytime a 1 came up, he guessed right. So on this quiz, he got 1, 2, 3, 4 questions right. So his score was 4 out of 10. All right, didn't pass. The next one, he got 1, 2 of them right, 2 out of 10. Okay, so that's not passing either. And then on the third one, he scored 0 out of 10. There's no 1s in there. So his score, the teacher would then look at each one of these and decide if he passed. So in this case, in our first simulation here, he didn't pass. He never got 6 out of 10. So the first question says, describe how you could use a random number generator to perform 1 repetition of the simulation. So we said let 1 be the represent a correct answer, and then the digits 2, 3, and 4, they'd represent a incorrect answer. And then we'd want to pick these. We could put these in a hat and shuffle them up and do 10 times where you pick one of those 4 digits. Okay, if it's a 1 to a 4, all right, then that's gonna simulate the results of guessing the answers to 10 multiple choice questions. We're gonna count the ones. This count represents the number of questions he got correctly out of 10. Then he takes the quiz 2, so this was quiz 1 here, quiz 2, and quiz 3, and then the teacher records the highest out of all of those. The dot plot shows Darren's simulated quiz scores in 50 repetitions of the simulation. So 50 repetitions means 3 quizzes 50 times. Okay, the dots represent the highest of the scores. So for example, in this simulation that I did, the highest score was a 4 out of the 3. So that would be represented using a dot over the 4. So this question is asking, well, explain what the dot at 1 means. The dot at 1 represents the average repetition where the highest of his 3 scores is 1, or 1 repetition where the highest of the 3 scores is 1. And there, that in that drop-down menu, that is our choice. Now, the second part says, use the results of the simulation to estimate the probability that Darren will pass. Well, to pass, he has to get a 6 or more. So if we look up here, out of the 50 times we did the simulation, 1, 2, 3, 4, 5 times, he had a score of 6. So to calculate that, we can say that there was 5 times out of 50 repetitions that he passed the quiz. Therefore, Darren has a 1/10% chance, or a 10% chance of passing if he is guessing on each question. We conducted a taste test for 4 different brands of chocolate chip cookies. Here's the two-way table that describes which cookie each subject preferred in that person's sex. Suppose one subject from this experiment is selected at random. Find the probability that the selected subject preferred brand C. Okay, so if we look at this, we want to know, well, what's the probability that they like brand C? So we're going to take all of the participants, total number of people in the survey, so we took the total number of people in the survey, which is I added up the number in each one of these cells. That's how many people participated. Out of those, the number of people that liked brand C were 13 and 11, so that became my numerator. And I end up with 24 over 94. And when I divide that out, it says round it to 3 decimal places. So the second 5 is the third decimal. I look at the 3, it says leave that 5 alone. So my solution is 0.255. Okay, the next one says find the probability that the selected subject preferred brand C or is a female. So when we see the word or, we know that we're going to add the probabilities. Okay, and if these two events were mutually exclusive, then that would be it. However, these two events are not mutually exclusive. You can be a female and prefer brand C at the same time. So then over here, we use our general addition rule, where we're going to take the two probabilities, add them up, and then we're going to subtract the overlap. So in our case here, that would be the probability that you prefer brand C. All right, so the probability of brand C we did, it was 24 out of 94. The probability of being a female, well, there's 94 people altogether, and then the total number of females would be 4 plus 6 plus 13 plus 13. Okay, then we've got to subtract out brand C and a female because we've already counted it once. That was this 13 right here. So then we would subtract out that probability, which is 13 out of 94. Now you could have done it like this, and now we would just add those up and subtract and then turn them into a decimal. Okay, or you could have done this as just one whole fraction where my numerator would have been 24, 36 minus 13 divided by 94. And when you do that addition of those, you get 47 over 94, which is 0.50. So here's my formula for a conditional probability. As soon as I see the word given, I know that I'm going to be dealing with a conditional probability. Here's my formula. So I want to first do the denominator, which is the given part. What's the probability of being a female? And if I look at my chart up here, if I'm a female, then there was 4 plus 6 plus 13 plus 13, a total of 36 females. Then in my two-way table, I'm going to look for the cell that is female and brand C. Okay, well, female and brand C would be the intersection of female and brand C, which is right, let's change the color here. So that's the intersection of the yellow row and this blue column, which is 13. And then my ratio is 13 to 36, which comes out to be 0.361.